All right, I'm sharing my screen now. So let me know if you're not able to see anything on your screen or not able to hear me. Yeah.
We can't. Okay.
All right. So just to recap the assessment percentage. So test will be 10%, assignment 15%, lab 15%, and your final exam is 60%. So your lab 1 report will be due this Friday. Yeah, I give you until this Friday. So submit by this Friday, and then next week will be the binary equation report due on next Friday also, right? And I think there will be no test.
Or Wednesday?
Sorry?
The deadline, is it Friday or Wednesday?
Initially, before this, we say, I think Wednesday, right?
Yes.
Yeah.
Yeah.
So maybe we stick to Wednesday if all of you ready, or you want to do it Friday.
For me, I already submit, so it's okay for me.
Okay, all right.
Not
How's
sure.
Oliver and is cool here?
I think I haven't submitted yet, but I'll be submitting later.
Okay, yeah. So let's stick to Wednesday. Let's stick to Wednesday as what we agree earlier, right? Wednesday, yeah. Okay. Yep. Okay, let's do chapter 4. So chapter 4, we have 3 main items here. So we'll learn about laminar and turbulent flow, and then after that we learn about friction loss in laminar flow and turbulent flow. Yeah. So let's learn a little bit concept about what is laminar and turbulence. So as an engineer or those learning science, we need something to quantify a behavior. So when we talk about laminar flow or turbulent flow, we will look at one individual parameter. We name it as Reynolds number. So this Reynolds number, we're going to define whether your flow is laminar or turbulent. Reynolds number given by this equation that you see on the screen here. Reynolds number equal to rho Vd divided by mu. So rho is density, v with the head is average velocity, d is the diameter of the pipe or the channel divided by viscosity. This is dynamic viscosity. Yeah. All right. So let's look at one video about the behavior of laminar and turbulence flow. Are you able to see the YouTube on the screen? Yeah.
Yes.
Okay. Hold on, yeah. Okay. So what you're seeing here is that the experiment is running a water. Then you'll see a blue color ink coming out from the middle here. So if the flow is laminar, you're going to see a ink coming in a straight line. If not, then you'll see there's the color change, like a mixture of color in the water here. All right, so maybe I need to fast forward. You'll see that you see the color, the water color change now to blue color. And then now you see that there's a line over there in the middle of the video. So now you see that the water color is blue, meaning there's a mixture of the dye and the water. And now in the video, you will see some blue line in the center over here. So if you see a blue line, means that you're having a laminar flow. Yeah, having a laminar flow. This is a dye experiment. So this is a turbulent flow. And if you see a straight blue line, means it's a laminar flow. Yeah. So this is a laminar flow. You see a line there in the middle, in the pipe, mean that you're having a laminar flow. And if you're seeing a blue water, means there's a mixture of water and the dye there. Okay, I think sufficient for the concept. Yeah. So by having this, if you look at this video and back to the slides that we see just now, and you look at the formula of your Reynolds number, Reynolds number equal to rho Vd divided by mu. So this is the first equation for today, and it's a very important formula for the rest of the chapter because we're going to look at laminar and turbulent flow. So this Reynolds number is having four unknown there. One is rho, one is velocity, one is diameter, and one is the viscosity. So the rho is the rho of the fluid that you use. So what will change the rho is the pressure and the temperature of the experiment. Velocity is the velocity of the fluid here. D is the diameter of the vessel that you use or container that you use. So normally the D will be fixed. Yeah? And the viscosity is due to is linked with the friction, or the not friction, is due to the medium or fluid characteristic of the fluid itself. All right. So remember, there are four parameters that are able to affect the pipe flow regime, whether it's laminar or turbulent flow. Just give you a hint, not hints, but if you look at the photo on the screen here, we have a pipe and we have an entrance and outlet here. If you see the entrance, you are given by a symbol of all this arrow with the equal length. It means that you're having a uniform flow. If you're having this well-distributed arrow, it means that you're having a uniform flow coming in from the left into right, and then you're having a diagram that you see in the middle of the pipe. We call it a velocity profile. Velocity profile, that you will see that as the flow go very near to the wall, and you know that as there's a contact between the fluid and the wall, there's a friction, and the friction will capture the fluid molecule stop from moving. So you will see that the value of velocity when it's very near or near to the wall or at the wall, it will become zero. Yeah, it will become zero. Then it will start to pick up the speed. Yeah. So this is the velocity profile diagram. So by the end of this chapter, you should be able to plot or describe the velocity profile of the flow. And then after the entrance length at a certain length of L, you're going to reach a phenomena. We call it fully developed scenario or fully developed region. You will get a parabolic profile, right? A parabolic profile. So in the later section, we are going to develop equation to define this parabolic shape later on. Yeah. So this you're going to be, you will see this diagram many times. We'll repeat seeing this diagram many times. We're going to define this shape later on. And our reference axis is from the center of the pipe. From the center of the pipe, you can see the axis over here. We have the axis is beginning from the center line of the pipe. And our y-axis here, we will use a radius. Radius from center, we denote as r. Yeah, we denote as r. So expect seeing something in the term of x in a term of R, in a term of small u, capital D, and sometimes you will see capital U with the zero, sub-zero here. All right, sub-zero means the entrance velocity. If you see the U means the velocity at that particular location. D means the distance or the diameter of the pipe. Okay. All right, there are one magic number that you should remember for Reynolds number, which is 2300. If your Reynolds number is less than 2300, you can define that you are having a laminar scenario. Then you use equation for laminar situation. Meaning start from chapter 4. Every time you solve question or solve exam question or assignment question, you start with Reynolds number. You define whether your flow is fall below category of laminar or turbulent, because once you either are able to identify the flow regime or the flow category, you're able to direct yourself to the correct equation, because we have one set equation for laminar flow, one set equation to solve for turbulent flow. So remember this magic number, Reynolds number less than 2300, you are having a laminar flow. Now some books, some textbook, if you go into aerodynamics textbook, you'll be seeing Reynolds number less than 2100. Okay, so for this module, we will accept value that below 2300, you can consider as laminar flow. Okay, so some textbook will use 2100. Some textbook, the textbook that I use for this module, the author used 2300, which is still acceptable. Yeah. All right. So this is the number that guide us to the type of laminar flow, to the type of flow that we have. If it's less than 2300, we get laminar. If it's more than 2300, means we have a turbulent flow. All right. Yeah. So it's not 230. Normally we will take 4,000, about 4,000 to become turbulence. Yeah. So maybe maybe you just mark that we use 2300 as a transition point. Yeah, transition point. Maybe 2300 it's not correct that you say that. Yeah, it's not say that 230 is a transition phrase. So in transition, you will have a mixture of laminar and turbulent flow. Yeah. So remember this magic number. Normally we'll use 4,000. Right now, redox number more than 4,000, then you have a turbulent flow. Any question for this magic number and the Reynolds number that you have?
No.
All right.
No, sir.
All right, good. All right, then we look at an entrance region, which is from here to here, that what you see on the screen, and I highlight with the box here. So if you're seeing that there's a uniform, there's a equally length of arrow coming in from the left. This region we call that is an entrance region with the laminar flow. We will study laminar flow first, and then we will go into turbulent flow. All right, and then yeah, this is what we seen just now. And to get this profile where the velocity at the wall here is 0, we assume that we are having no slip condition at the wall, but in reality there is a slip condition. But for theoretical derivation, mathematical derivation, we assume that we don't have a slip condition, yeah, so that we have a 0 velocity at wall there. And then for incompressible flow, we will use conservation of mass to define the speed over here. Right? So recall what is conservation of mass that we learned in the previous chapter. And every time you see the incompressible flow, you should always remember that the density doesn't change throughout the equation, the derivation of equation. And we're going to study, or we're going to learn that the equation for this profile. So from the diagram you see here, as is near to the wall, the velocity gets 0. As is near to the center of the pipe, you get a maximum velocity over here. Okay, so what we learned today, the first equation, Reynolds number. Second is on the boundary condition that you have when you derive for equation, yeah, for especially when it comes to velocity profile, you always need to use a boundary condition. What I mean by boundary condition means at a certain location, what is the u value? At a certain location, what is the u value? So a very direct boundary condition is that at the wall here, your u equals 0. At the center of the pipe here, your u is maximum. Your u is maximum. Later, we will have an equation to derive this one. And if you look at the axis that we have earlier, if your r equals 0, if your r equals 0, you get u max. U will become maximum. If your r is increasing until the maximum r, or your d divided by 2, or your r, capital R here, your u will become 0. So you have a two boundary condition here. One is at the center, one is at the wall there. All right. The next one, the word fully developed. The fully developed, it means that the velocity profile that you have inside the pipe doesn't change. All right. Even this section or that section, it will become same profile. So before this length, before this location, you will get a velocity profile that keep changing, right? Keep changing until at a certain length, you will get a fully developed profile. So when the question mentioned derive equation for fully developed velocity profile, it means that you're having a constant shape of velocity profile after a certain length. Yeah. Yeah. The next is the definition for entrance length. Entrance length, it means from the beginning for your inlet up to a certain distance where you get fully developed profile. This is the entrance length. Yeah. So sometimes the question will ask you to get the entrance length first. After entrance length, you will proceed to derive the equation for fully developed profile. For laminar flow, there is a number that you can always catch or focus on. If you have a laminar flow with the entrance length of L, you can write in terms of Reynolds number. Again, recall what is Reynolds number. RE equal to rho Vd divided by mu. The ratio L over D equal or very near to 0.06 Reynolds number, then you will have a laminar flow. L is from here to here. L is your entrance length. The ratio between your entrance length and D is when the ratio is 0.06 Reynolds number, then you are having most of the case you will have laminar flow. So there are two methods that you learn this afternoon to define what is the region or how you guess the float profile or the float regime. So how you know it is a laminar flow? The first you check the Reynolds number, rho Vd divided by mu less than 2300 or 210. In this chapter, we use 2300. So if the number is less than 2300, you are having laminar flow. Another case, if you are given the L and the D ratio, L and the D means the entrance length and the diameter of the pipe, you're able to calculate the ratio. From the ratio itself, you're able to see whether if the numbers is 0.06 Reynolds number, then you are having laminar flow. Okay? So this is there are two ways to know what type of flow you have in that pipe. One, through Reynolds number calculation. Second, through the length and the D that you have. So the first equation, Reynolds number, what is the application or how we ask you question in exam? Is that after you calculate the rho you can find in the appendix A. All right, so by this moment, you already need to know what is appendix A. Every time I mention appendix A, you should already have appendix A in your computer or somewhere in your notes. So in appendix A, you can find what is rho, what is the dynamic viscosity, diameter will be given, velocity will be given, or at the end of the solution or the question, there will be one particular section ask you to find the average velocity in the pipe. So once you find the velocity, there will be a particular section ask you to explain the flow regime that you have. So after you get a V, you calculate whether you are having laminar or turbulent flow. Another question for this equation that we see is that after you get your Reynolds number, the question will go ahead and ask you, design the dimension of the pipe so that you are having laminar flow in the experiment. Okay, I want you to try to get the idea how we test you in the coming exam. Yeah, so the first equation is to the first Reynolds number equation. Normally, the question will go to ask you when the question asks you to find velocity. After you find the average velocity in the pipe, from there the question will continue to ask you define the type of the flow you have inside the pipe. So the next one, you use Reynolds number and then use this magic number to explain whether it's laminar flow or turbulent flow. The number, if it's less than 2300, then you're having laminar flow. The next question will be, is more on the design, pipe design question. After you get Reynolds number with its distance, it will ask you, what is the entrance length or what is the minimum entrance length that you need to reach laminar flow or to achieve laminar flow? So you use this equation, L over D equal 0.06 Reynolds number, and then you move the diameter to the right, you're able to capture the entrance length. Yeah, clear? So far, there are two equations for today. Reynolds number and the laminar flow, L over D ratio. Okay, and recall, recall how you calculate average velocity from your Q. Q is your volume flow rate. Q equal to V times A, speed times the cross-section area. So you rearrange the Q equation. V equal to Q divided by A. So the next question is, what is the entrance length if the flow is laminar? So you need to know how to apply this equation, right? And these are the side note for you. It's very important. Reynolds number equation, rho Vd divided by mu, and 2300, this magic number. Okay. If you calculate, right? If you calculate based on 2300 number, so 0.06 times 2300, you will get 138 D. Yeah, it's cool here. Who's still not here? All right. Any question for how to get 138D? Any question want to ask me?
No, sir.
Yeah.
Yeah.
All right,
No, sir.
Oliver, you all right?
Yeah, right, sir.
All right. So this is how we get the L, the L for laminar flow. Yeah. So for it is if the exam asks you to define the entrance length, you write this equation, you get 1 mark, and then you apply the concept of laminar flow by using Reynolds number. You continue with the derivation. You get L equal to 138, and then replace the D value that you have in the question. The next one, just recall Reynolds number equation, rho Vd divided by mu. Reynolds number less than 2300, we have a laminar flow. So we're going to look at a few scenarios. The first equation, the first scenario, we're going to look at fully developed laminar flow between two parallel plates. Right, two parallel plates. So meaning two parallel plates means that we assume that we are not having a tube, but there's a plate above, there's a plate below. Plate above and plate below. So we are having this question. The flow between parallel plates can be the simplest form, simple experiment setup. The next question is that how or what makes the flow flow? What makes the fluid flowing? Yeah. So meaning if you have a two plate, what makes the flow can flow? Yeah. Okay, maybe I will let you guess. All right, Oliver or Amir, if you're having two plate, what do you think that the flow will able to move from the left to right? Maybe Amir, you want to try?
If I'm having what, sir?
Yeah, so the question is this one. So if you're having a parallel plates, right?
Yes.
So you're having a parallel plate, top plate and a bottom plate, and you fill in with the float. You're having a float in the middle here. So what make the fluid flowing from left to right? What contribute to the flowing of the fluid? Fluid in the middle here. What contribute or what can move the flow? Or what should you have to move the flow?
Pressure, right?
Pressure. Okay. What about Oliver? What do you think? Or maybe I draw something like that. I draw two plate, this orientation. What do you think the fluid will going to flow like that?
Should be pressure.
Yeah, pressure. What else? What else that make this flow down?
The gravity.
Okay, gravity. So I think most of you are able to guess. So the first is the pressure, which is a pressure gradient. The change of pressure there's a pressure difference between the left hand side and right hand side. or between the both end of the plate. The second one is you either move. There are two plates, right? So either you are moving, this one is stationary, this one is moving. So if you move the fluid, if you move the plate, top plate or bottom plate, in this case we move one plate on the top, the flow is going, the fluid going to flow. Logic? Does that make sense to you?
Yes.
Yeah. All right. So these are the second scenario that we're going to look at. The first, we're going to look at the pressure gradient. The second one, we're going to look at what happens if you move one plate. What is the equation to derive for the velocity, and so on. Yeah. And the fluid, we assume we're having a Newtonian float. Yeah? Newtonian float. Yeah. All right. The third one is what you guessed just now, is because of the gravity or body force. Right? Body force is or gravitational force. So you're going to look at these three scenarios. And there's another one, maybe there's a combination of these three. Any of these three, maybe the pressure plus the gravity or the pressure plus the moving plate will also contribute to the movement of the fluid. Right. So if you understand this, you're able to capture the rest of the concept for the next few section. All right. So the first one, the one that you see on the screen here, the first one, remember the Reynolds number, which is the first equation that you learned today. Second one, there's another equation, which is the L over D equation. And then the magic number 2300 that define the flow region. 2300, less than that, you become laminar flow. And we love laminar flow, right? We love laminar flow. So this is a very important numbers, 2300. Then we're going to look at what is the mechanism that make laminar flow happen. First, the pressure gradient or the pressure difference between 2 points, gravity, and also moving one of the plates that transport the fluid. All right. Let's look at the first scenario where we have a plates stationary first. Yeah. So if you have a both plate that doesn't move first, we look at doesn't move. Both plate that doesn't move. So one example that you see on the screen here is what happened in the cylinder, piston cylinder that you have in your engine, car engine. You look at the diagram, that bottom diagram, you have a two wall here, which is the engine block here. And then you have a piston that move up and down. And then if you view from the top, you will see that outside circle is the cylinder block. And the inner circle is your piston. Then after that, you use a microscope to zoom in this section. You will see that actually there's a few fluid gap between the piston and cylinder. The gap is very, very small. All right. Now this scenario, we can simulate as parallel plates in a scenario, and we will see how we derive the equation for a laminar flow inside this piston. Yeah, so the gap is very small in our assumption. So the gap is 0.005 mm, or I will use a 5 micron. 5 micron. All right, 10 minus 6. 10 micron meter, 10 power 6 meter. Yeah. So we can model as this kind of flow. We can model as infinite parallel plates here. Okay. So if your gap between two plates or two walls, the gap is very small, and there's a fluid flowing between them, we can assume that we're having a parallel plate scenario. Then to calculate the leakage flow, or the flow is flowing through the gap when the engine moving. Yeah. So we will start with velocity field. It is U. We going to start derive equation now. So the diagram that you see over here is actually we rotate the diagram over here. We have a top plate and bottom plate. And then we have a center line between the two plates, like what you see just now. So we have two plates, and then we have a center line. And the gap between the two plates is given by A. And you're having a center line axis here, which is the X prime and Y prime. The location of, or the distance from the wall to the axis is A divided by 2, which is center of the gap. We have Y prime and X prime. So we have another axis here that you see on the diagram here. You have X and Y, which is your reference axis. If later on in the equation you see Y, X without the prime, it means that you refer from the wall. You start from the wall. So if your equation, you're having a Y and X, meaning you're calculating from this point towards the center. All right, meaning you have, if your Y equals 0, it means that you're at this location. If your Y equal to A divided by 2, it means you are at the center. Okay, just recap what we learned this morning. Oliver, what is the speed at the wall? What is the speed U at the wall? Oliver, are you there?
Yeah, yes, sir.
Yeah. What is the speed at the wall? What is the U value at wall here? Or I change the question. I give you see the diagram. What is the value of U at Y equals 0? Or here. What is the value of U at this location? Y equals 0. What is U value?
Is 0, right, sir?
Y 0? What's the
No,
reason?
sir. The stationary part.
Yeah, what
wall.
contribute to 0? Your flow is flowing. Your float is flowing from the left to right. But why the velocity at the wall is 0?
I'm not really sure, sir.
Amir, are you able to answer why you're having a velocity 0 at wall? Amir, are you there?
Yes, sir.
Yeah, why velocity at wall is 0?
Not sure, sir. So Y equals 0, right?
Yeah, at y equals 0 here. Why the velocity 0 at wall?
At the wall?
Yeah, why the float velocity is 0? Why here is 0?
It's because like it starts from the middle, then it goes.
Yeah, what? Why? If you pour water, why the molecule doesn't move at the wall? If you pour water from the left to right, when you measure the velocity here, why the velocity of the water is 0 here? And there's a flow at the middle. You get a U max at the center. Why?
Not sure, sir.
What physics tell you? What physics concept you have? What does the friction do to the? What is the surface do to the float? What happen if you have a molecule?
The force goes
moving,
to the
and
others.
there's a stationary surface here. Stationary surface. What
To
happens
the
if this molecule touch this surface?
friction force.
Yeah. So again, for Oliver and Amil, so why we get 0 here is because of the viscosity effect and because of the friction between the contact between the fluid and the surface.
So the flow concentrating on the middle, right?
Again,
The flow concentrating on the middle.
there is no contact here, so the molecule is free to move at the maximum speed.
Okay.
Right? There's a viscosity. You understand viscosity?
Yeah.
Yeah. So if there's no resistance over here at the center, you can say that there's no resistance at all at the center. So you can move at the maximum speed, or if you're coming in 10 meters per second, at the middle, wherever you measure at the center, you'll get 10 meters per second. Assume you're having a Newtonian float. Understand, Oliver?
Yeah.
Okay. So this concept is important because it's going to affect the derivation steps for the next section. All right, so U equals 0 at here, at Y equal to center, Y equal to A divided by 2, your U equal to U max. All right, this is a concept that you should learn from today's lecture. All right, so when I write Y prime equal 0, what is the U value? Amir?
At y equals 0, the u value is 0.
No. When I write Y equals 0, your U equal 0.
Yes.
When I write Y prime equals 0, which axis that you are referring to? We're having two kind of axes here. One is Y, what is Y prime?
Yes.
Yeah. So if I write, do you see there are two axes in the diagram here?
Yeah, y and y prime, yx and
Yeah.
y.
So when I write Y prime equals 0.
So u equals the max, u max.
Yes, correct. U max. Okay, another question for Oliver. When my Y prime at the wall, Y prime at raw, what is the value of Y prime? When I use second axis here, when I write Y again, repeat your answer.
No, you said Y prime at wall, is it?
Yeah, now if I want to define this location, what is my Y prime value? By using this diagram, what is your Y prime value?
Is it 0?
Do you see there is
value, there's an X prime value.
where is your y prime y-axis located? Here, right? Do you see
Yeah.
this one?
Yeah.
I'm asking about this distance from
Oh,
here to here.
it's
When I ask about
A
wall,
A over 2, is it?
yes, correct. Y over 2. When I say y prime.
Yeah.
Okay. What is the velocity at y prime a divided by 2? What is the velocity here?
Is 0?
What's your answer again?
Is it 0?
Y0? Why you say is 0? What do we discuss just now? Why you get 0? Why the velocity becomes 0 when it reach
Because
wall?
of the frictional force.
Beside friction, what is the fluid property that affect the velocity?
Was it Newtonian fluids?
Okay, Newtonian float. One of the parameter for Newtonian float, what is that? Reynolds number. What is this? What is this term? Rho Vd divided by mu. What is mu? What is this?
What's it called?
Amir, can you recall what is this?
Viscosity.
Correct.
Viscosity.
Oliver, what is that? What is this?
Viscosity.
And this one is dynamic viscosity. Yeah.
Yes.
You have two type of viscosity. Yeah. Another symbol is like that. It's called kinematic. Don't confuse between dynamic and kinematics. Yeah. So later on, we're going to convert dynamic viscosity into kinematic viscosity. So at the moment, we stop at a dynamic viscosity. All right. So far, I keep repeating the concept. What is U? What is U max? And so on. Yeah. So you should. There is we call it boundary condition, which is important in your mathematic derivation. Boundary condition. So there are two axes. Yeah. So one is y x at the bottom. One is y prime x prime. So when I mention y equals 0, it means it starts from the plate here, from the wall. Velocity 0. When I mention y equal to a divided by 2, it means your this axis reach this portion. U equal to U max. I extend this question again. Y, when your y equal to a, what is the velocity? Oliver, this question is for you. When your y equal a, what is your u? What is your velocity?
0?
Correct, because it's at here. Huh?
Yeah.
All right. So when I mention y prime, it means you look at this axis equals 0. You're having u max because it's at the center. When I have y prime a divided by 2, it will be 0. U will be 0 because it's reached here. When I want to say this plate at the bottom, I will use y prime equal negative a divided by 2 because I go down. I will get u equal 0. Clear? In all these terms. When I mention boundary condition, you should know which axis that you are referring to. We have y, x, or xy plane, and also y prime, x prime. And in exam, you write the boundary condition, you will contribute some marks there. By just writing this boundary condition, you will contribute some marks. So these are the way you score marks in your exam. All right. Okay, let's go for a few more slides. Then we have a break. Yeah. All right, so we stop at this diagram. Yeah, and recall what you learned in the previous chapter. We call it a control volume. So we draw this very small cube as our control volume. The size of this control volume we define as dx, dy, dx, dy. So these are all the notation. Distance A is distance between the plate, and we're having infinite in z direction, means the plate is coming out from the screen. We assume that we're having a steady and incompressible case in this derivation. The boundary condition that we already explained just now. When y equals 0, u 0. When y equal to a, u also 0. Because when you reach the top, you get 0. Okay, let's see the first equation. So another mathematical model, so you're right, u equal to uy, it means that the u is changing in y direction. Okay, the u is changing in y direction. And we'll look at fully developed scenario. And when we derive the equation for both plates are stationary, our v vector, w vector equals 0, meaning we don't have velocity vector in y direction and z direction. We only look at x direction for velocity. All right. All right. And the pressure difference, we know that we have three mechanisms that make the float flowing: pressure, gravity, and moving plates. There are three concepts: moving plates, pressure, and also gravitational force or body force. So the first mathematical equation, which is so basic, we calculate the volume. So the volume of the control volume will be, you take dx, dy, and dz. Product of these three, you get volume. V with the middle line inside there to represent volume. Momentum equation, recall, so this one you should already familiar. Momentum equation, we look at force developed from second Newton law, F equal to ma. So we have two terms or two components that contribute to the force in momentum equation: surface force on body force, and what happened in the control volume and control surface. So this one should be familiar. And remember, your test one, I haven't asked you this one. So can say 100% are going to come out in your final answer. So make sure you're familiar with u rho dv and u rho v dot dA. So what happened to this one? Yeah. So we're having an assumption: steady flow, fully developed, and there's no body force at the moment. So steady flow, we cancel the first one. Means if you have steady flow, there's nothing changed in the control volume for the rho, for the u, and so on. Right? Having the first term u equals 0. And then we don't have body force. We take out the body force component. You only have the surface force in x direction and what happened in the control surface here. And remember, when you look at control surface, you look at vector, velocity vector and area vector. So to get equilibrium scenario, your Fx will be equal to 0, which means all the force acting on the surface will be 0. So this is equilibrium scenario. Yeah. And then after that, we look at this diagram. So all the force acting on the control volume over here. All right. Let's see. Yeah. So you look at the control volume, and at the center of the control volume is having a pressure, and the shear force, the shear stress acting on this point is given by shear yx. I already explained the sub y and x earlier. If you're not sure, go back to the video in maybe chapter 2 or chapter 3. Go back to the chapter. I explained about sub y xy. So how you get pressure? Pressure equal to force divided by area. When you mention pressure load or pressure force, when it mentions pressure force, it means pressure is pressure. Pressure equal to force divided by area. When you talk about pressure force, means that you're calculating the force created by the pressure is pressure times area. All right, now let's look at this diagram. What is all this little differentiation equation means? I will explain about the negative dx divided by 2. So why there is a negative dx divided by 2? The length of the cube here to here is dx, and there's a dot at the center of your cube here. So if you move to the left, the distance between the center to the left wall here, you take dx divided by 2. If you move to the left, because all direction to x to the right is positive, y moving up is positive. So if you're moving to the left, mean you have a negative sign there. Negative dx divided by 2 because it's half of the dx. Understand? Any question on this one, Oliver?
Can you just slightly explain it again, sir?
Can you repeat again also? Didn't really catch it.
Okay. All right. Now explaining why you are having negative dx divided by 2. What is the size of this cube earlier? This cube, the size, we know that our x is to the right, positive. Y is going up, positive. The size of this cube is dx dy. All right. And you have a dot in the center of the cube. So you know that the length of the cube is dx. From the center to the left face here, it should be half of your dx, correct? And you are moving to the left, you know that your axis positive to the right. If you move to the left, you get negative. That's why you get a negative dx divided by 2. Is it clear?
Yes, sir, okay.
Yeah,
Oliver, clear?
yeah, clear.
So when you look at the right hand side here, you get a positive dx. You should understand why there's a positive there, because it's moving to the right hand side. You get a positive, and it's half of the dx. All right, now why you get this del P over del X? What is this? It's the differential of pressure, the pressure difference that on this side. because at the center of the cube, if you move to the left, there's a changes of pressure, or we write del P del X. There's a change of pressure in X direction. This is the Taylor series or Taylor series definition. You times the distance traveled by the molecule, or by the distance, or by the molecule, right? The distance you travel from the center to the left-hand side surface is negative dx divided by 2. When you time this one, you get the changes of pressure, or del P, if you move to the left. Understand? Understand this one?
Yes.
Yeah. Yeah. So that's why every time you move your pressure to the left, you'll get a lower pressure on the left, because yeah. All right. Then you have dy and dx here, and then you times P plus the differential of your pressure here. You get the pressure term, the changes of pressure. And just now we define pressure equal to force divided by A. So force equal to P times A, pressure times A. So what is the area of this face here? Area of this face is the length of this one will be your dy. And to find the area, we need the dz here. So you take dy times dz, you get the area. So the force times area, the pressure times area, you get force. So you understand? The products of this one become force already. This is area. This is pressure. Understand?
Yes, sir.
Yeah.
Oliver, clear?
Yeah.
So same with this one. Same with this one. All right. Now, since we are only looking at X direction, yeah, although you can claim, oh, there is a pressure this way, there's a pressure this way. Yes, we have, but you're not looking at the vertical direction at this moment. We only look at X direction, right? Now, another things that will happen in the Newtonian float, yeah, is the viscosity that created the shear loading. Do you understand what is shear? Shear load or shear stress?
Yes, sir. Yeah.
Yeah. Shear, it means the force is go parallel to the area here. Means this combination, you get shear stress. So again, you're taking stress. Shear stress, it means that you take force divided by area. Only the force direction that is parallel to the area, you get shear stress. It is this one, right? Right, so you have a positive and negative here. So you understand why you get dy divided by 2? Y on the top you get positive dy. Y at the bottom you get negative. Do you understand? Oliver and Almir?
Yes, sir.
Yeah. So it's the same concept like just now. Now you change to y direction, y distance. And this one del y times this one is the changes of the stress. Yeah. Okay. Now you want to get the shear load, we call it, or shear force. What you take shear stress times area, you get shear force. So again, you take your shear stress times the area, you get the shear force in X direction. So by looking at this diagram, you're having 4 forces that in acting on the control volume in X direction. Understand? It is because of the pressure and shear stress. Any question on this diagram?
Yes.
Clear?
No, sir.
Clear? Clear?
Yes, clear.
Yeah.
Yeah.
Oliver, clear?
Yeah.
All right. So this component on the left, we write DFL. It means pressure force at the left-hand side, left face. We get this term. Pressure on the right-hand side, we get this term. We write as DFR, right faces, this one. And then the shear stress at the bottom, given by this component, we write as DFB is a force. So, but this force is created by the shear loading, shear stress. You write F capital B, it means bottom. You have a negative negative sign there. Understand why it's negative? In this diagram, you do not see negative. Why there's a negative when you write force? Why in the diagram here, there's a positive sign here? Oliver, you understand? Why when you write the shear force in a mathematical term, there's a negative in front of the magnitude. It is the magnitude. Why there's a negative there? Or in the diagram here? Yes, correct.
Direction.
Correct. You see the direction is going to the left, right? So you get negative there. So be careful. Sometimes the question will ask you to draw the forces on the control volume. Sometimes the question will ask you to write in a mathematical form. So be careful not to confuse between the negative sign in a mathematical model and on the diagram itself. On the diagram, all is positive value. Yeah? All is magnitude is positive. What is different is the arrow. And how to draw the arrow is fixed already. Yeah? From the left is from left to right. For on the right hand side is from the right to left. It must be balanced. Right? It must be balanced. And the shear stress top is from the left to right. Bottom is from the right to left. Be careful on the direction. Same with the top also. Shear force on the top surface, we have a positive sign. We denote as DFT equal to positive shear force. Okay. And we know that the whole system is balanced, or we call it equilibrium scenario, mean that all the four forces that you see just now, the dB, dt, dl, dr, you plus these four together equals 0. You sum all of them together, you arrive at this equation. Okay, you arrive at this equation. You will get d shear yx divided by dy equal to dp over dx equal a constant value. Make sense? Does it make sense to you?
Yes.
Right. Then you'll get, when you integrate this equation, means you pull your dy to the right. Then you integrate, you'll get shear yx equal to dp dx y plus a constant value c1. Recall earlier we defined Newtonian float for shear equal to mu du dy. For Newtonian float, the shear stress yx equal to mu du dy. You replace the term of shear stress over here with mu du dy on the left hand side. You integrate again to get the u. Our intention here is to get the u. What is u? U equation. You integrate this equation, you get u equal to half mu dp dx y square, because you move your mu to the left. You move your mu to the left, 1 over mu. You move your dy over here, you integrate with the y. You get y squared divided by 2. That's why there's a half 2 here. Plus, you integrate with y. Constant value, you add a y behind there. And remember, you carry the mu to this 2 term here. That's why you see C1 divided by mu y plus C2. Understand why you get this equation, or how you get this equation?
Yes.
Oliver, is that all right for you?
Yes, sir.
Okay. Now you have a 2 constant value here. To solve these 2 constant value, we will use the boundary condition that we discussed, I think 30 minutes ago. All right. So we use a boundary condition to solve this C1 and C2. They were put on the screen here. Y equals 0, u 0, y equal to a, u equals 0. Means that you put 0 and a in the equation here, u 0 and so on. Yeah. So you use these 2 boundary conditions, you're able to find what is C1 and C2. So you'll get C2 equal to 0. You do the max, you do the max as your homework. When you apply the boundary condition, you'll get C2 equals 0, C1 equal to negative half dp dx a. After that, you substitute inside this equation, you get a full equation for velocity profile. I'll show on the screen here. Right? If you substitute these two, C1, C2, you get u equal to this term plus this term. You rearrange for a better analysis, means you put all the constant value to the left hand side with a dp dx outside, and then you write in the ratio of y divided by a, so on. This is the velocity profile equation for both stationary plates. So this is the equation for today's lecture. Right, we stop at these slides. And let me stop the recording.